Okay, I'll start. Okay, I know most of you here, except Dhruv Patel, have had a formal logic course. Dhruv, I understand based on our conversation, you've had a course in digital logic. So your approach will be different. But even for people that have had a logic course, I believe that for you to sit through the 3 lectures, I expect to spend about 3 lectures on the logic recap. Would be useful to attend it and attempt the first assignment on Z3 because I'll be talking about a little bit about using logic to model artifacts, including programs, that you might find it somewhat different than what you see in a logic course. And as I said, I want all of you to use Z3 to check. Z3 is a SAT checker to check a model and check some of the problems that I'll be assigning. Okay. So, logic, of course, you could study logic just for its own sake, for the interesting kinds of properties and structures and properties that it does. But in this course, our intention is to use logic to model programs and programming systems and specify their behaviors and use logical reasoning to analyze properties about those programs and also do it in an automated fashion. Okay. So, given that, I will be talking about more about program semantics, different ways we can use logic to model behavior of program, but to just initiate you into the thing. Let's suppose you have this two statement, a program fragment having 2 statements. Here, you could, what it means to model the effect of this program. One way is to each of these conjunct here models a specific, the program, the effect of this. So I'm using logical variables here, time-stamped, indexed logical variables to denote the value of x and y, the 2 program variables, as they vary as you execute each instruction in the program. So, for example, x naught and y naught are used to denote the value of x and y at the start of the program, the entry point, and the index variables are used as they to denote the value of the variables as they after every instruction. So the first instruction, the effect of first instruction can be modeled by this equality in the logic. X1 is equal to x naught plus 1 as it increments the value of x. And similarly, y, after, once this assignment is done, the value of y after execution of the second statement will be y1, which is equal to 2 times whatever the value of x was at the start of the second program instruction. So put together, which is the conjunction, one can say that it gives the overall effect of the program. That is, it relates the state of the variables at the entry point to the state of the variables at the exit point. So in that sense, this can be the thing. So I mean, yeah, this is what logic has logical, I mean, variables in them. And that is what is being used here to construct the effect of the program. Then the other component of verification, as we discussed in the first class, is for you to specify the expected behavior, which could once again be specified in this case. We're using the same logic. I mean, one of the things we want to ensure is regardless of what the initial state you start from, this will always ensure that the value of y at the exit point is even, okay, by virtue of the fact that you're multiplying it by 2. So that if that is the property, the behavior that you want to ensure that this program satisfies, then your specification will be something like this, that the value of y1, the variable, the logic y1 should be this. Then you want to somehow express the fact that this behavior implies the specification and ensure that by means of using logical reasoning, using the rules and the calculus that logic provides you. And you want to do it in an automatic way. Okay. So given that, yeah. So there's only one small notation that I'll be using. So not like you said, we already have, even to talk about program semantics and in logic, there are variables and you have to talk about the values that these variables take. And that is what we call as valuations, the values assigned to these variables. And these variables can range over various domains and depending upon the logic that you use. So, for example, they can vary over Boolean, true, false, or some other domain of interest, say, for example, integers. And then valuation is a function that assigns values to each of the variables. Okay, so for example, x and y could be true and false, and z could be taking 23. I mean, you could write it this way. Sometimes we want to kind of update, as you go along, this valuation functions, and that is expressed as, or you want to substitute a particular variable, change the value of that variable. So in that case, we use this notation. So here, sigma is being, you could say, is an x is being substituted with a new value. So sigma, and this denotes a new sigma, which is exactly the same as the old sigma for all variables except x, where x takes the new value y. Okay. Okay, given this, okay, now what is yeah, okay. So you can talk about different types of logic. Okay, some of this thing does not work. Okay, okay. So we'll be talking, yeah. So logics can vary in their expressive power and deductive power. By deductive, I mean the reasoning, power. And I mean, these are different kind, and the domain over which the variables can range, and the way they get this expressive power is by means of these features. So if the domain is restricted to true and false, then what you have is prepositional logic. Sorry, there is a new line missing here. Or you can have logics that allow you to have the domains be like first order domains. By first order domain, I mean they can be domains like natural numbers, integers, real, etc. And then you get first order logic. Okay, so sorry, the new lines are missing here. So from propositional logic, you can get to first order logic, and one of the features of first order logic is that the variables there in that logic are allowed to range over, other domains, possibly infinite. Now, from there, you can go to higher order logic, which, if the variables, if you allow from first order objects, you allow for domains to take functions, relations over first order objects, then you have logics which are usually referred to as higher order logic. Okay. The other way the logics vary is whether you have quantifications over variables allowed. Okay, this was again allows, increases, enhances the expressive power of the logic and the complexity of the logic as well to decide the truth value of these assignments. So quantifications can be, for all or existential, okay, over first order variables in first order logic, first order predicate logic, these quantifications, I mean, yeah, they're ranging over first order variables. Whereas in higher logic, then if you extend the quantifications to range over sets and functions over the first order domain, that is supported in higher order logic as well. Then you have, specialized logics, okay, which are tailored to express the behavior and properties about restricted systems. For example, temporal logics talk about, they hear what kind of connectives that you use and to express the temporal logics. They are specialized logic once again to tailor them to describe program behaviors which are expressed as by expressing constraints over traces. And whole logic, here I'm listing two logics which are tailored to describing, improving correctness of programs in a somewhat limited way. Okay. But there are lots of different kinds of specialized logics, even when they are applied to analyzing program. I mean, some of you might have heard separation logic, which is suited for analyzing correctness of programs with pointers and so on. Okay, so this is just a quick overview. And in the recap, primarily, we will be in this course, we'll be dealing with the propositional logic, first order predicate logic, and later on these two kinds of logic, temporal logic and whole logic. And in the logical recap, I will be covering prepositional logic as well as and first order logic, and then getting to temporal and whole logic later on in the course. Any questions so far? Okay. Okay, so this is the outline for the next. I don't think I'll be able to cover all of them today. I hope to introduce you the prepositional logic and modeling with prepositional logic, and a little bit of how one can automate reasoning in prepositional logic, and basically what happens inside a SAT solver, a checker, and continue with predicate logic and its automation in the next few lectures. Okay, for pedagogic reasons, okay, All of you have taken the logic course would have seen this. Maybe Dhruv hasn't, so that's why I chose to do it in a pedagogic way. Whenever you introduce logic, it has two main components. Okay, the first is the syntax, which describes how you construct the syntactic rules that determine how various syntactic structures, which end with formulas are constructed. Formulas are constructed in the logic. And the second component is semantics, which gives the rules as to how you assign truth values to all these well-formed formulas, syntactically well-formed formulas as in the logic. So, prepositional logic, Dhruv, you might have been introduced as Boolean logic. It starts with here I say infinite set of atomic proposition, but for any given formula can only have any finite formula can only have finite set of atomic propositions, which are like variables ranging over true and false. Okay, so you may put it as finite but unbounded set of atomic propositional propositions, or sometimes I call them as propositional variables. Okay. And then you can have, so that's what P is, P denotes. And then you can have, depending upon your choice, constants, okay, to denote the truth value, true and false. Here I denote them as top and bottom. And then you have various logical connectives, so the atomic formulas can be either a proposition P, which can take true or false as its valuation, or the constants true and false. And then you build bigger formulas using using logical connectives. Now, here I have, just for example, I have, there's the negation connective, the and, the or, implication, equivalence, and this is exclusive or. Okay. Now, you can have other Boolean, propositional connectives as well, but for illustration, I've just shown these three things. Sometimes you only have a subset of these things and there is this notion of universality, because everything else here, in this case, implication, equivalence, and exclusive or can be expressed in terms of not and or, as you guys probably know. But yeah, so sometimes you restrict propositional logic just to these three connectives. You could. So those are stylistic variations. Okay, any questions? Okay. Now, next is how you the semantics part, and this gives the rules as to how you determine which formulas that are constructed as per the syntactic rules are true or false. And since our formulas start with have prepositions in them, the prepositional variables, the truth or false of a formula that contains variables is determined by the valuation, the values assigned to those propositions. And that's why these truth assignments to formulas are parameterized with respect to uh, this valuation sigma, which in this case, it maps each preposition variable to true or false. Here, the true false is the truth, the logical truth, okay, which is distinguished from the syntactic constant top and bottom, okay. Yeah, so given a formula, semantics assigns it can be atomic formula or something non-atomic constructed, by applying these logical connectives to smaller formulas. Okay. So, and the rules of semantics, they are defined recursively. Okay. Where you first define the truth value of the atomic formulas, the first three rules, and then, sorry, I think it's sensitive. And then here, in the last set of rules, can be considered as giving the semantics of logical connectives, which are described by giving the truth value of a compound formula in terms of its sub formulas. So as you would expect, the constant true we intend is always intended to be true, and therefore it is irrespective of what sigma is. It is always true. Bottom, which is the constant false, is always false. So P is a propositional variables that depends, its truth value depends on what the value that your valuation assigns to P is. And that's why its truth value is defined by applying sigma to P. And the rest are all as you would expect, okay? Given values assignments to the variables, not of phi 1 is true if phi 1 under the assignment as per sigma is false. Otherwise, it is false, and so on. Okay, so here I do, yeah, and says the usual. I mean, it is true. This formula, if both phi 1 and phi 2 are true under evaluation sigma, and so on, or if either of them is true, and so on. So I imagine that this is should be clear, to you. Any questions here? Or am I going too fast or too slow for you? So I assume there are no questions, so I'll proceed.
Sir,
Yes.
sir, in that slide, the third last statement, uh,
In this line?
Q1, yeah, Q1 implies Q2, phi 1 implies phi 2 uh,
Mm.
under sigma. So, is that only one case, like Q1 under sigma false and phi 1 under sigma false and phi 2 under sigma true?
There are two cases here. If phi 1 is false, then it is vacuously true. That's the first case.
Yeah, and the other case is the both
Oh,
are true.
it is if otherwise, that is, if phi 1 is, yeah, it is true if phi 1 evaluates to false, if phi 1 evaluates to false, or it is whatever the phi 2 is, right? Why is there an otherwise? There is no otherwise here, right?
Yeah, yeah.
Yeah, yeah, yeah. I think this is redundant. Okay, there is no otherwise here. These are the only two possibilities. Correct. Yeah, false and yeah, phi 1 can either be false or true, and therefore the first two cases captures, and there's no need for otherwise. Yeah. So I think otherwise is needed here. Yeah. Even here there's no otherwise. I don't know why there is I put the otherwise symbol here. Yeah. Yeah, because these two cases capture um, the whole thing. Correct. And Correct. That's the right observation. Yeah. Yeah. So, for any given valuation sigma that assigns truth value for the propositional variables in the formula phi, if I, those valuations that make the formula go to true become true, then such an valuation is sigma is called a model or a satisfying assignment for five. And these are the three important.
Sir, could you please go back to the previous slide once? Yeah, I'm sorry, how did the implication, why the otherwise false is not needed, how this two is covering everything? Because what if phi 1 is false and, sorry, phi 1 is true and phi 2 is false?
You're right. You're right. Okay, so I'm just going things. Is this Kathakali?
Yeah, yeah, yeah.
Yeah, yeah. I think otherwise is needed, guys.
Otherwise it's
Okay,
needed, I
so
thought.
If yes,
Phi
yes,
1,
you're right.
phi 1 is true and
She's
phi 2
right.
is
You're right.
false.
Okay. What I mean, I was silly. Yeah, because there are three cases where if phi one is false, then it is vacuously true.
And phi 2
If
is true, it is
phi
obviously
one
true.
is true, there are two
True.
cases. No,
Yeah.
phi two
Sir, I think
occur.
there are three cases.
Yeah, three cases. Phi two, if phi one is true, or
And phi 2 is
if
false.
phi two is true, then it is true.
Yeah.
Otherwise, it is false. Okay, that's the third case. You're right. Yeah,
Yeah.
correct. Yeah, I correct myself again. Yeah, you're right. So, yeah, there are three cases. Yes. Yeah, for people who have taken logic, these are kind of easy, and I think yeah, if you still have questions, you can always ask during the course of recap, and if I'm going too fast. Okay, so there are three notions. One is if the validity, satisfiability, and unsatisfiability. If a formula is true for all possible valuations, okay, since although we allow infinite set of propositional variables, given that the formulas are of finite size, they can only have at most a finite number of variables in them. Therefore, the all possible valuations are indeed finite for a particular formula. So you can have, if a formula is true for all valuations, that is for all models, then it is said to be valid. Okay, sometimes this is also called when in Boolean logic a tautology. It is satisfiable if there exists some model, there's some satisfying assignment that makes the formula become true. And it is unsatisfiable if there exists no model for which it is true. Okay. So these are the three important notions of satisfiability that you have for propositional logic. And a SAT checker is an algorithmic way to check these three, given a formula, to check these three things. I mean, here's where, even if you allow infinite things, these algorithms are supposed to check satisfiability for a finite, set of all finite formulas. If you assume that the number of variables, your formulas are finite size, of course there is a trivial, I mean, algorithm, a naive algorithm, where you can, because all valuations are finite, given that there are only finitely many propositions occurring in a formula, you can enumerate all valuations and check them for each valuation. That is how, you call that the truth table. And you can make a truth table and do it. But modern day SAT checkers use a lot of a lot more sophisticated algorithms with a lot of heuristics to make it quite efficient in practice. Okay, and we will get to that later. I don't think in the logical recap, I don't think I'll only be giving an overview of a SAT checker. The important thing is, I want you to use Z3 and then check all the problems in there, so you'll get a feel for doing it hands-on. Okay, so that is the problem of SAT checking. It is decidable, but it is as it's an NP complete problem. It's complex even for finite things. Okay, so I want to switch gear here and then get to how we could use even propositional logic, as simple as it is fairly expressive to be able to model various artifacts. I mean, various quizzes and problems, games. I mean, you could model with propositional logic. Okay, and even finite, programs, as long as your variables range over discrete finite domains, you will be able to, propositional logic is sufficient for you to, is expressive enough to model. Okay, so I want to give you a flavor of that, what it means to model with propositional logic. And here I will use, I'll switch over to another set of slides. Okay, so here is a problem of deciding a seating arrangement. We have three people and three chairs. Those three chairs and three people to be seated in those chairs with some constraint on how they can be
The
seated.
sir, screen is not.
Okay, okay. Whenever I do this, okay. So here are the constraints. Okay. The people are numbered as one, two, three. Okay. And the first constraint says that person one and person three shall not be seated next to each other. Okay. And the chairs are numbered too, we can assume. So every person must be seated in some chair. And the third constraint is no more than one person shall be seated in a chair. Okay. These are the three constraints. The question is, if it is, yeah, so then you can ask various questions, each of which the idea is we want to be able to model this problem as a satisfiability problem in propositional logic. Okay. So then you can ask various questions and then have them model them in propositional logic and get them as satisfiability questions and use a SAT checker to provide answers and solutions for these things. can ask the question, is there a feasible seating arrangement such that each constraint or each constraint is met, or a combination of all the constraints are met? Okay, so that is a satisfiability question. So once you are able to express each of these constraints as formulas in propositional logic, you you could then, if the question of is there a feasible arrangement can be expressed as if there is a satisfying solution for those constraints. Then you can say, if so, what are the possible seating arrangements? That is, extracting a model that satisfies the formula. Are they seating? Yeah, and then you can ask if there are seating arrangements that are not able to satisfy one or more of the constraints. Okay, that will be an unsatisfiability thing. And is are all the constraints met by every possible seating arrangement? Okay, so then it would be a validity question. Okay, um, so before you, yeah, so there are two parts here. One is, I mean, the big part is how exactly do you model this? So each of these constraints have to be modeled. Okay, as you know, a proposition formula starts with propositional variables, right? So we have to start with some, define what the propositional choice of your propositional variables. Okay, so for example, you could start by introducing a variable xij. So for I between 1 and 3 and j between 1 and 3. So which denotes, which is assumed to be true if and only if person I is sitting in chair j. Okay. So as you can see, there are only finitely many possibilities for these, okay, situations, and therefore, and that's the reason, because there are finite number of chairs, a finite number of people to be seated, you can model this these constraints using a finite number of propositions. And the choice of your proposition is very important. Okay, you may have, for any given problem, lots of different way of choosing your variables, and your encoding of the problem, the constraints in propositional logic, how the size could be very well determine what variables that you choose. This is not what I'm saying is it's not the only choice of variables, and how you choose and how exactly you model. There is a great deal of ingenuity, there. Okay. So let's see how we could model for this choice of variables. Okay. So the first constraint, which says person 1 and 3 shall not be seated next to each other. Okay, that's the first constraint. So that can be modeled as it cannot be the case, it should not be the case that x12, both x12 and x32 can be false, right? Okay. Yeah, so it should not be the case x12 or x32. Those are the only two ways that that violates that constraint. Okay, and are you okay with that? Believe that?
Yes, sir.
Okay. Every person must be seated in some chair. Okay. That can be modeled as at least for every I, at least one of them has to be true, correct? Is that a, uh, you know, Is this a good way to model?
I mean, it does say that some every person sits in some chair, but two-person can sit in a single chair as well. Something like that might have.
Yeah, that is there. But this even allows, if you think about it, for xi1 and xi2 to be true both at the same time, right? So it even allows, by modeling it like this, it allows for the same person to be seated in two different chairs because this is true when it's not exactly saying exactly one of them has to be true, correct? Okay. This is by modeling it as a logical disjunction. It is true even when xi1 and xi2, or actually all three of them are true. What does it mean for all three of them? Well, that's what it means. Okay, so I is here is person I. Okay, so person I can be, yeah, so you're right. Okay, what you said is right. So it allows for more than one person to be seated in the same thing, but that can be fixed by adding this one. At most one person shall be seated in a chair. Okay, so by adding these two things, then you will get the effect of being exactly one person is seated in every chair, and every person is seated, certainly seated in some chair. I leave it as an exercise for you to define this. As a matter of fact, you can define exactly one, at most one, at least one, all of them once you assign what the meaning of a propositional variable is. So this is the idea, okay? And the other key point that I'm trying to make is when you model these things, you have to take care so that so whereas the constraint phi 1 is the real constraint, certain other constraints will have to be thought through carefully as well. One can easily miss certain trivial constraint that, okay, the problem may not say that every person has to be seated in a chair, and you will take for granted that every, no two-person can be seated one over the other. Okay, so this exercise of modeling, okay, itself, there are two aspects there that will bring more precision to your problem. So you may discover that you might have missed certain constraints that are important for your problem, that you might have missed it when you state it informally, that'll come out, okay, either during the modeling process or when you actually use SAT checker for checking, finding solutions. And the other aspect is, as I already told you, there is no one way to model these things, and some, depending upon the connectives that you use and the choice of the variables, these encodings of these constraints, even in the same logic, can the size of those encodings can vary, and therefore this aspect of encoding is has to be done carefully, especially when you are modeling large exercises like huge programs or big problems like Sudoku and even other complex games. Okay, that's the problem that I'm making. And then once you define the variables and then you model the constraints, then of course the idea is to use SAT solvers to check these logical constraints and get solutions for them. So satisfiability, if you use checking satisfiability, then you get, is there a feasible seating arrangement, okay, that satisfies all these constraints? That can be expressed as whether phi 1, phi 2, and phi 3 is satisfiable. Okay. You can throw this problem at Z and Z3, and then it does come up with a not only answers if it is satisfiable or not. If it is, then it comes up with a model. Okay. Or you can, if you want to then generate one or more feasible seating arrangements, then you'll have to enumerate the different models that NZ3 does provide facility features for this, or you could program using Z3 interface, API interface to generate all the models as well to get all possible seating arrangements. Or if it is not satisfiable, if there is no possible seating arrangements, then it can answer that it is not satisfiable, that it is unsat. Okay, all these things are possible with Z3. Okay, what I want you to do is, as a first exercise, I mean, I have already uploaded the GUI instructions link to the GUI instruction. I mean, a link to using Z3 in a GUI mode. And, this problem is small enough that you can try it in a GUI mode. I will also upload a link to a Python interface to Z3, and some of the problems on my first exercise with Z3 on logic exercise will be, some of them will be pencil and paper for those who want to, get a refresher in logic. And each of those, some of them you may have is large enough that you may have to use the programming API to write a program, because sometimes if the problem is large, the number of variables, as you can see here, the number of variables is 3 times 3. There are 9 variables. So if you want to solve the 8 queens problem or the Sudoku problem, all of which can be expressed as satisfiability problems in prepositional logic, the number of variables that you have to use can be quite large. And generating these encodings for the constraints that you want to express, it will be too unwieldy to write by hand. Okay, and then that is why the API comes in handy, where it provides various functions and things to, primitive functions to build your formula, and then invoke SAT or unsat SAT queries into the thing. I will have one problem that will require you to use the API interface as well. I mean, that is a little bit more complicated, but yeah, I mean, certainly the pencil and paper one, and as many of the problems that you can solve using the GUI interface, I want certainly all of you to do, especially those that think that they have limited. I mean, they want to. They have not had a formal logic course. Okay. Any questions so far? Yeah. Okay. So moving on, I will. This I'm going to skip. Okay, because these are some, simple exercises. Okay, so I'm assuming that all of you here, the audience, have Boolean logic or the thing. So, here are some examples that give the satisfying assignments for these formula. But what I want to get at, given the time that we have here, is the next set of problems. Okay, so this is probably this notion is probably familiar to you, but I want to emphasize this because throughout, especially when it comes to modeling software behavior, program behavior, using logic, this is important to see formulas as predicates. Okay, predicate is just a Boolean function, functions that map their arguments to true or false. Formula can also be viewed for denoting sets and relations. Okay, and you can use these things interchangeably. And I want you to, even people who are familiar with logic, I want them to be comfortable with this notion. Okay, so here we have a formula phi 1. Okay, this is a formula over three variables, x1, x2, and x3. So you can view that formula as a representation of a Boolean function that maps triples, okay? The values x1, x2, x3, Boolean triples to true or false, okay? So it's, in that sense, it's also can be considered as a Boolean function. A Boolean function, a function whose range is true or false, is what is called as a predicate, okay? So every formula in propositional logic can be considered as denoting a Boolean function or a predicate. It can also be considered to denote a set, okay? Here as a set of triples, okay, and where the set, every element of the set is exactly the triple for which that makes the formula, in this case phi 1, to be true. So, for example, the formula phi 1, denoting the predicate phi 1, is true for these three. These are the three satisfying assignments for x1, x2, and x3. These are the set of all models that of phi 1. So when I say, when we say a formula or a predicate, what does it denote? It is assumed to denote the set of all satisfying assignments for the formula. Okay. Given that, then you see that you can do so. If the trivial formula true, well, obviously, if it is considered as denoting a function over three variables, it denotes the universal set of all Boolean triples. Okay, that's what true will be considered as denoting. False, obviously, it'll be denoting the empty set. Okay, simple. Okay, so but still is something that you need to be aware of. Okay, it gets a little bit more interesting if when we start doing this. Okay, so let's take the example of modeling an assignment statement as a relation. Okay, okay. So predicate formulas, is that clear? The way I define what the set that it denotes. Any questions there? Okay. So here's a simple assignment statement in C. I assume X, capital X here to denote a bit vector, and greater than, as you know, is right shift. X is a bit vector of size 2. It right shifts the input. Actually, I think I might have implemented as left shift. Left shift. Let me see. Okay, although I have written as right shift. So the assumption is it shifts it with 0 moving in on the left. Okay, so that's what we are supposed to model. Like I showed in the beginning slide, you can model it as a relation that relates the state of the value that of the bit vector at the beginning at the assignment and after the assignment, pre and post the assignment. Okay? So now here I'm defining it as using a once again a predicate or which is has four variables: x1, x naught, denoting the value prior to the assignment, and the primed variables x1 prime and x naught prime as post variable. Okay, and I'm saying x naught prime. Yeah, so this should capture the effect of shifting it right. Okay. And with, yeah, shifting it right means x naught prime. Okay. This should be true whenever the primed variable captures what the effect of shifting it right and moving a zero to the most significant thing. And that's what this captures. X naught prime should be equal to x1 and uh, x1 prime should be false, okay, because zero is moving in there. Now you can see you can extend this to an arbitrary, a finite but arbitrary sized bit vectors, by using enumerated conjunction. Okay. But for illustration, we will just use the uh, two-bit thing as illustration. Okay, what does this denote? If I this predicate, anybody? Here I've instantiated x1 prime to be 1. What does it mean to ask this question? What does this denote as a predicate?
Uh, should this be false because we are in that statement we are saying that not x1 prime?
Yeah. Who's this? Can you introduce
Uh,
yourself?
Lucky sir.
Lucky. Yeah.
RAM.
Yeah, you're actually right. Here I made a mistake. Okay. Let's suppose that it is doing a left shift. Okay. So you're exactly right because I'm using right shift. So no matter what, did what Lucky said, did the rest of you understand? So basically, what I'm asking is, okay, actually, Lucky's answer was correct given what t is, okay? Because this can never be true because I'm right shifting and I'm saying that I'm moving zero to the most significant bit, which in this case is x1 prime. So when I say this, you can say, oh, is this satisfiable? Okay. But I asked this question in a very specific way. What does this denote as a predicate? I just now defined a formula which denotes a predicate is supposed to denote, as per my definition, the set of all satisfying assignments. Okay. So in this case, given what the way I've defined T, this is false. This is unsatisfiable. So what does it denote? It denotes the empty set. Okay. Let's suppose that I had defined T as left shift. Okay, with zero moving in. For the moment, I'm sure we can change T for that. Then what would this predicate denote? Anybody? Intuitively, what it does, and well, there are lots of people who have taken logic course. No answer? See, this is important. The reason I brought up modeling as the thing is you need to definitely feel comfortable with this. Okay. So let me uh, provide the answer. See, it is actually like I'm running the program backwards. It is. So once again, I'm noting that I've changed T to be left shifting. Okay. So in that case, this is set of all 2-bit inputs that result in the most significant bit of the result, where the most significant bit of the result is a 1. That's what. Those are the exactly the satisfying assignments of, I mean, those are the satisfying assignments that of this predicate, okay, which is denoted by the left shifting thing, okay. Left shifting means I'll have to make appropriate changes. That are you guys convinced now? Okay, so this denotes 1 1 and 0 1. Here once again I'm assuming T is being shifted to the left. So this is how, okay, we view formulas and predicates, and then we assign the meaning for a predicate as the set of all satisfying assignments. So in that sense, this is denoting a input-output relation of executing a single statement by relating the formula, and the predicates is relating the input to the output. And then once you do it like this, you can ask very interesting questions. Um, what are the outputs that you get for a set of inputs, or what are the inputs that for which there are you get certain kinds of outputs, and so on. So by using this, okay. Now, given the same thing, once again, I'm assuming it is left shifted, or you can ask this question for right shifting also. Is this satisfiable? Okay. Now I have a sequence of instantiation of this transition relation T, okay, where each T is successive T is fed the output of the previous is fed the sorry, yeah, yeah. So what does, when I say, firstly, is this satisfiable, and then what does the set of all satisfying instances of the above formula denote? Any thoughts? Now, this is a formula, okay? So let's suppose I instantiate K for 2. So I'm starting with T11 BV1 and BV1 to T BV1 to 0 0. Okay. Suppose I make K is equal to 2. So suppose I have it as T11 BV1 and T BV1 comma 0 0. What does that denote? I've already explained what T denotes. This is the effect of executing the program that statement once, right? So you could consider this too long thing. If suppose this assignment, the assignment statement here was inside a loop, and then you were executing it multiple times, then you could having two instances of T1 where it is being fed as executing it twice. That is the effect of right shifting or left shifting it twice. Okay. And if you're doing this K times, then it means that you are asking the question, if I right shifted it k times, if I executed this right shifting operation assignment statement k times, and if I started with 1 1, is it possible to end with a 0 0 value? Okay, and that can be the thing. Okay, so given this, if say I'm doing left shifting rather than right shifting, what are the values of k for which such a sequence formula? Okay. Firstly, is my explanation clear? Or if not, you will have to stop me and ask question. Are you convinced what I said? Anybody?
Yes, sir.
Have I lost you? Where have I lost you? So if I did say left shift two or more times, something is there on the chat box. I don't think, Ayan, if you're speaking, you're not audible. And Gyanishi says no.
Sir, that operator is correct, right shift it is.
Yeah, say right shift. Okay. So suppose we assume it's right shift. Yeah. So in this case, it is whether it is right shift or left shift doesn't matter. Okay. So in order, if you're doing right shift, let's suppose you say right shift. So if you did two or in two shifts, you will get 0 0. Correct? Yeah. If you have 0 is moving in. So the correct answer is this is satisfiable for all k greater than or equal to 2. Correct. Yeah. That's what I am expecting. I mean, am I right? So, so
Yes, sir.
yeah, this denotes this is true whenever, yeah, yeah. I mean, this is true whenever you have this assignment statement being executed. So, in that sense, if this were in a while loop, what this denotes is kind of the trace, you could say, because as long as there are intermediate values b1 through bvk minus 1 such that this constraint is satisfied, then you have it. Okay, then this will be true. Okay, and that's what this thing denotes. Now if I had put XX here, okay, it could be any arbitrary BV0. Okay, I should have put, if I put an arbitrary BV0, then, even then, as long as you've executed it for two or more times in the loop, this would still be true. Otherwise, it would be false. So, so I hope you got the concept that you can now construct more complicated formulas involving this thing, and then make it model the behavior of programs. But all of them, regardless, okay, that is one way. I mean, what it means to model a program. I mean, I'm giving an inclination, but here, the thing that I want you to be comfortable, get acquainted, and then comfortable with is this notion of formulas denoting defining predicates. Okay, and then and what it denotes is a predicate. When I say what it denotes, it is the set of all satisfying assignments. Okay. So if I had replaced 1, 1 with BV0, then this sequence would be a set of all possible traces. Okay. That would result from starting with some arbitrary input bit vector as the initial value and then executing it k number of k number of times. That's what this would mean. So in that sense, this would be a trace. It would be modeling the set of all traces of executing this assignment statement in a loop. Okay, so that's what I want you to be, the key takeaway of this thing. So I'm going to stop here and I'll continue next time. So I want to, before I end, um, next week it will be a physical class, okay, not online. So I want to propose that if it's okay with if we meet at least for next week from 3:30 to 5, okay, or 3:30 to 4:45, okay. I will announce the room after checking what room is available, but time slot Tuesday, Thursday, 3:30 to 5. Is that okay with you?
Yeah, it works for me, Professor.
Yeah, what I will do is I will.
For me as well.
For
Yeah,
me as well.
I don't know how many people are seriously planning to take it, but nonetheless, at least for the first couple of weeks, I want to keep it. If there are some people who are undecided and that they want to attend a few lectures and then decide, I want at least the first week and the first couple of weeks until the logic recampus thing to make the slots flexible. So I will send out an email, and if it is inconvenient for you, then with two options, okay. And then if one is inconvenient, the first option is not possible, you have conflict, and you still want to give it a go and then attend. For each of those options, let me know by return email only if it is if it is convenient or not convenient. So that thing. So by end of tomorrow, Friday, if you can intimate, then it'll be useful. Yep. Okay. Do you have any questions before I end the lecture? Okay. If not,